hello everybody. Welcome back. And today we will continue our work energy methods. And we will start with a brief lecture overview, right? Because yesterday, I believe Professor Sani showed you another variation of work energy equation, yes? And then we will do example number 1 and example number 2. So let's start with our brief lecture review. So this is what we did last time, right? We derived this expression. Yep. We started from this expression, and we ended up with this expression, where this was work of all forces. Yes, we didn't assume anything about forces acting on our particle. Yes, we just said that there are forces acting on our particle, and that's it. Yes. By the way, as just a small digression, last time I was a little bit hesitating if this force is net force. Let me maybe go here and here. Yeah, I was not sure if this force is net force. Yes, it is. I spent some time at home on thinking. Yes, this is a net force. Yes. Because 1 hour after your discussion on Wednesday, I said to another group I am teaching that I am not sure if this is net force, and I might have made the mistake with you. No, I didn't. This is a net force. Okay, just to clarify. So I actually made a mistake with them, not with you. Yeah. All right. But today, so this is what happened on Wednesday. Yes. Today, we will start with exactly the same equation, F equals to ma. However, today, we will just divide our forces in conservative forces and non-conservative forces. So, we will again repeat the derivation steps. We will start with projecting our equation on our trajectory. We will have analogous transformations, and if you do it at home, you should end up with such equation. T1 plus U12 of conservative forces plus U12 of non-conservative forces. And this is equal to T2. Okay, so very similar expressions, as you can see. Yeah, very similar. And now, this guy, if we look closer at this, and if we integrate all the conservative forces, we can actually end up with such expression. This is equal to V1 minus V2, where this is difference in potential energies. And this guy we'll just treat exactly in the same way we treated it last time. So this will be basically U12 non-conservative. So this is work of non-conservative forces. Work of non-conservative forces. Okay, so this is the other version of our expression. Of our work energy expression. This is T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. Okay, and we will use this expression today twice. Any questions? All right, so maybe you guys can give me some examples of conservative and non-conservative forces, okay? So let's start with conservative forces, okay? So we can do like examples of conservative forces. Let's make a table. Yeah. So what force we can classify as conservative force? What force do you know that is for sure conservative? Spring. Okay. Let's start with gravity. Okay. Spring will be second. Gravity. Gravity. So we have mg. This is our force associated with gravity, and our potential energy will be mgh. Let's say where h is elevation, of course. Then you said linear spring. Linear spring, where force associated with linear spring is kx, and potential energy associated with linear spring is, potential energy will be 1/2 kx squared. Yes, and there is, I think this semester you can also encounter cubic spring. Cubic spring, where force associated with such spring is kx cubed, and potential energy will be 1/4 kx to the power of 4. I don't know. There might be some other conservative forces you can run into this semester, but I don't recall any. I don't know. We will see. And if there is like force that is not in our table, you will know what to do with it. I have no doubts. Okay. How about non-conservative? Okay. Anything comes to your mind? To your mind? Yeah. Friction, let's say. And as kinetic, okay? Kinetic friction. Kinetic friction, and our Tf is equal to mu kn. Yeah, and then you have to just integrate that expression, yes, along the distance. So usually the U12 non-conservative of Tf will be mu k and times some distance, yes. Oh, of course, with a minus, yeah, negative, yeah, with times some distance. Okay. Another non-conservative force is, of course, applied force. Applied force, which is F. And it can be a function of time, a function of position. I don't know. You will have to integrate given force. And third one you can encounter this semester is aerodynamic drag. But very rarely. And usually there are different models for aerodynamic drag. However, this is like the basic one. Some constant times velocity squared. And maybe some other examples. Questions? By the way, this is the most common model used in modeling friction. However, recently I had a conversation with one of the professors from Texas, and he spent like the last 10 or more years in tribodynamics, so science that deals with friction. And he said that this is not true, that friction is way more complicated than that. Yeah, you seem surprised. Yeah, why are you surprised? Yeah. Yeah. So this is what we are using, and this is probably what most people in industry are using. However, the friction to model friction correctly, we should use probably different models. Yeah, but we're going to use this model. Just a digression, okay? Any questions? Or example number one? So let's do example number one. As usually, please familiarize yourself with the problem statement before we start our solution. Okay, so what do we have in here? Aha, we have a ball, yes, that has mass m, right? It has mass m, and it is attached to a spring, yes? And that spring is pre-compressed in configuration 1, yeah? It's pre-compressed by delta 0. This is delta 0. And it is released from rest, yes? So velocity initially 0, and here in configuration 2 they will separate, yes. So our ball will stop touching the plunger, yes, of the pinball, yes. And they asked us to find k of that spring, so I should put k also in here, k of that spring, so that our pinball has certain velocity. And what do we know? Aha, we know the weight of the body. We know the initial pre-compression. We know that system starts from rest. Obviously, it has to start from rest. If you not played pinball once in your life, you know that it has to start from rest. And we know the velocity final, yes? So we can call it actually velocity F, maybe velocity final. Why not? Velocity final. Okay, and let's find spring. Okay, solution steps. And if you would like to, on the exam, for example, yes, or in your life, because yeah, these methods also work not only on the exam, yes, they also work when you model systems outside of this course, yeah. So, but okay, on the exam, please go for this recipe. Okay, let's start with this first step. T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. This is our first step, okay? And you already have 1 point for that, okay? Now, let's find these 5 guys, okay? So let's find T1, V1, T2, V2, and U12 non-conservative, okay? Let's find these 5 guys. So what is T1? The kinetic energy at the beginning. It has to be 0 because system starts from rest. Sys starts from rest. Okay, what is T2? It will be 1/2 mvf squared. Yes, because this is our expression for kinetic energy. Okay, what would be potential energy at the end? It would be 0. Yes, because our spring is not compressed. At the end, or it is also not stretched. Yes, so maybe our spring is at rest. Yes, spring is at its rest length. Is this correct in English? Thank you for nodding. Okay. So okay, how much of the problem done? 60%. So now let's do 80% of the problem. How about V1? That spring is linear, and that spring is pre-compressed. So just let's check the other board for the expression, but I'm sure that you remember. So the potential energy here will be 1/2 K delta 0 squared. Yeah, this is our potential energy at the beginning. Okay, so we have 80% of the problem done. Now let's go for 100%. We have to find this thing. U12 non-conservative. Are there any non-conservative forces acting on our body? I see one person shaking his head. Okay, there are no non-conservative forces acting on our body. That's why this is 0. No non-conservative forces in our system. All right, we found that 5 guys. Next step is to plug these guys back in to our original equation. Okay, so you already guys have like 4 points on the exam. Yeah, if you do that, I mean 4 out of 10 because I usually grade out of 10. So yeah, so now okay, let's plug this back into. So it will be 0 plus 1/2 K delta 0 squared plus 0. This is equal to 1/2 mv final squared plus 0. Okay, and this is one expression and one unknown because only this thing is not known. Only this thing is not known. One equation, one unknown. Okay, solve for K. And by the way, this is actually very characteristic to work energy method. We usually end up with one expression, one very long expression, okay, with some unknowns, okay. In the future there will be more unknowns in that one expression, okay. So we usually end up with one equation. However, do you remember in kinetics we ended up with like 4 sometimes and or 5, yeah. So yeah, that's the difference, yeah. So in here we have one equation but very long, but previously we had like 5 very short. Okay, yeah, so in here we just put everything into one basket. So K will be m v squared divided by v final squared divided by delta 0 squared, plug in values. So K will be approximately 0.178125 divided by 32.2 times 15 squared plus 1 divided by 6 square, and this is approximately 44.808 pounds per feet. Okay, this is answer. Any questions to what happened? Okay, that's it. This is how you use that expression. Easy? Okay, so now example number 2. As usually, please familiarize yourself with the problem statement before we start our solution. Can I have the attendance list? I can approach you. Anybody else is not on the list? No. Anna? Yeah. What's your name? Erin? Oh, okay. Usually Anna is there. Anna is not in here. And Will. Yeah, but not you. Okay. Okay. Okay, so what do we have in here? We have our configuration A, our first initial position, yes, and our pendulum is at this configuration, yeah. So our pendulum has mass m attached to its end. We have gravity acting downwards. Pendulum is released from rest, and this is the trajectory, yes, of our pendulum, obviously. Yep. So our pendulum will just lower its elevation, but it will gain velocity, yes. And they ask us to find this angle, theta, at which our rope breaks, yes? And we know how strong is our rope, yes? Our rope cannot handle more than 2 mg. Okay, so if tension in the rope is more than that, we don't have we have 2 ropes then, basically, yes? Yeah, 2 shorter ropes, yes? And they didn't tell us what is M and what is L, but we will introduce them, okay? And they will cancel out during our thinking process. So that solution. Any questions to the problem statement? Yeah, this is interesting problem actually because it combines kinetics and work energy, okay? So our part 1 will be kinetics. I told you last time that, yeah, that we are done with kinetics. It looks like we are done with kinetics, but it will come back all the time, yes? Or all the time, most of the time, okay? So what is the recipe for kinetics? First one is FBD. FBD, at some arbitrary configuration. At some arbitrary configuration. And of course, KD as well. So shall I copy that drawing? Maybe not. Let me draw it from scratch. Okay, so that will be our trajectory. So this is our rope, imaginary rope, yes, because actually on FBD we should draw only that dot, yes. So this is our particle. This is our angle theta. And what forces act on our particle? And the same drawing here, of course. I will copy. I will paste. What forces act on our particle? So you are much smarter than me. So I'll just start with the easy one, okay? Mg. And there is one more force acting on our system, which is tension. Yes. Somebody whispered, but I heard you. The tension. Okay. And this is curvilinear motion. Yes, this is not linear. This is not like rectilinear motion. Yes. So I would go for. You can go for either polar or normal tangential. Polar or NT. I'm gonna go for NT. Okay. I'm gonna go for NT. So let's go for UT acting this direction. And obviously UN will be acting this direction. And our accelerations will be MAT and MAN. All right. So now we should, second step of our procedure is EOM. So let's just write equation of motion in in 2 of these directions, okay? So sum of forces in NT with this direction as positive, and sum of forces in the N direction with this direction as positive. Okay. I know something broke with my OneNote. Just for some reason I can't erase this thing. Okay, we have to leave with this. Okay, sorry. Okay, on the T direction. Aha, so we have to do some projections, yes? So we have to project mg on this direction and on this direction. So this will be these are our projections. And if theta is here, I believe that theta will be also here, right? Because we have theta here. So that would be 90 minus theta. So theta will be here. Yeah. Okay. So this guy will be mg cosine theta. And this one will be mg sine theta. Great. We can write our equation of motion right now. So we just have mg cosine theta, and this is equal to mat. And on the n direction, we will have t minus mg sine theta, and this is equal to man. Okay, next step, if I remember correctly, was replacing at and an with these expressions. At was dv dt, yes, and an was v squared over rho. And very quickly, I need some help again. What is rho in our example, John? L, exactly. Rho is L, which is not known, by the way, yeah, but we will introduce it, and L is constant also. L is constant. So let's plug it in. We will have mg cosine theta equals to m dv dt. And also we have t minus mg sine theta equal to mv squared over L. Okay, I solved that problem yesterday, and this equation we can ignore. This equation does not tell us anything, okay? We will just focus on this equation. This equation does not contribute anything. This equation does not contribute anything. But we just did it for sport, okay? I just wanted to remind you how to do kinetics. So we ended up with one expression. And how many unknowns? Let's count them. I bet we don't know tension in the rope. I also think that we don't know V. And we don't know theta. Yeah? Or yeah, we don't know theta. That theta at which it will break, yes? So we have three unknowns. Yeah? Which? Yeah, I will count it, but it will cancel out. Yeah, so actually we have five, because m is also not known. Okay. However, they told us that our requirement was t equals to 2mg. Yes. They asked us to find theta star. They asked us to find theta star. Oh, shoot. Theta star such that t equals to mg. Okay, so let's maybe plug this expression in that one equation above. Okay, so we will actually have 2mg minus mg sine theta star, yeah, is equal to mv squared L. And you guys can see that m cancels out. Yes, we can get rid of m. So we ended up with 2g minus g sine theta star, and this is equal to v squared L. Okay, so again, we don't know theta star. We don't know velocity. And also we don't know L. Okay, so it doesn't matter. We have one equation and 2 or 3 unknowns. Okay, let's say 3. Okay, 2 or 3 unknowns. Okay, we need more equations anyway. Yes. Okay. So now what will come helpful? Work energy method. Okay. So let's leave our problem in here. Let's leave it in here, and now let's go to part number 2 of that expression. Part 2, work energy method. Okay. Yeah. So okay, we can count this one also as an unknown. Okay, L. Let's put it in like blue or something. Okay. I agree with you, John. I agree with you that it's not known. Yeah. Work energy method. Okay. So what was recipe there? T1 plus V1 plus U12 non-conservative is equal to T2 plus V2. Second step, find these 5 guys. T1, V1, T2, V2, U12 non-conservative. Bang, 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 bang. Okay, system starts from rest. Yes? 0 here. Great, 20% of the problem done. Oh, and by the way, by subscript 1, I mean initial configuration, okay? Initial config. And subscript number 2, I mean some arbitrary configuration. Some arbitrary config. Okay, so if I scroll up the board, guys, if I scroll up the board, T1 and V1 corresponds to this. Okay, and T2 and V2 corresponds to this. Okay. You know that, yeah, of course. Sorry, yeah. So what is T2? What is T2? At some other configuration, our particle has a velocity, yes? And we have only one particle, so it will be 1/2 mv squared. Great, 40% of the problem done, yeah? Okay, let's now go for potential energy. Anybody has any suggestions? What shall I put next to V1 and what shall I put next to V2? Maybe I should start with coordinate system, yes? Or yeah. Okay, you're right, yeah. I'm gonna actually do reciprocal of what you said, okay? Because actually, guys, before writing down V1 and V2, we should put datum or datum, yes, in our drawing, yeah? So let me scroll up the board. And you, Sanam, you wanted me to put my datum here, yeah? I don't want to listen to you. I want to put my datum here, yeah. This is our datum, okay? Yeah, this is our elevation 0. Elevation 0, okay? So, yeah, so now you can see that our particle is aligned with our datum, yes? So our potential energy due to gravity, so it actually will be, this will be just V1 due to gravity, and that would be 0. Yes, because our particle is at elevation 0. And V2 will also have V2 due to gravity. There are no springs in the system, in other words, yes? And I think that in here, our particle is below our datum, yeah? So what will be the potential energy of this particle? Okay, great. Great, awesome. Yeah, you're one step ahead of me. So it will be minus mgh, but you said that h will be L sine theta. Yeah, based on this triangle. Perfect. Awesome. So that would be exactly minus mgl sine theta. And thanks to Sanam, we have 80% of the problem done. Okay, let's go for the final 20%, okay? Are there any non-conservative forces acting on our system? John? Yes. Yep, it will be tension. So it will be U12 of T. Yep. So let me draw FBD very quickly. I can copy it maybe, or maybe not. So our particle was here, and on FBD only for non-conservative. Only for non-conserve. Okay, so I'm not going to draw mg in here, okay, because we took care about mg in this part, okay, in this part and this part. We took care of mg. Now only tension is left. It's interesting. What will be the work of that force? What will be the work of that force? So let us write integral from beginning to the end t times ds. Right? That was our definition on Wednesday, yes? Okay. And this is our trajectory. Do you see, guys, already what will be the answer of that integral? Our ds is always tangent to the trajectory. Okay? What angle is here? 90. Exactly. Our tension is perpendicular to ds. Yeah? So I'm not going to even ask you. This is 0. So our integral is also 0. So work of non-conservative forces is 0 in that case. Any questions? There was a question, Clara? Okay, so thanks to John, we have 100% of the problem done. Okay, what's the next step? Plug in these 5 guys back into our original equation. Okay, so let me write it down. So what will you have? I think that T1 was 0, V1 was 0, work of non-conservative forces was 0, and we ended up with this kinetic energy and this potential energy. Great. So we can get rid of M. And we just have that our V squared is equal to 2GL sine theta. Okay, so this is our second equation we found. Let's combine this equation with our previous equation. Okay, let's put it here. Okay, so we have such 2 expressions. And we must solve for theta star, right? So I'll put star in here as well. So I think that the quickest way is to express, look, we have V squared over L in here, right? So I think we can also find from this expression that V squared over L is equal to 2g sine theta star. Yeah? Yeah, and let's just plug this thing in here. And I think it should solve the problem. So we can just write 2g minus g sine theta at which it breaks is equal to 2g sine theta star. Yeah, I think that even g cancels out. Wow, g cancels out, and we end up with sine theta star equal to 2 divided by 3. So our theta star is arc sine of 2/3. Grab your calculators and obtain that this is approximately 41.810 degrees. Answer. This is the answer. And time for questions. Any questions? All right. So thank you for today and enjoy your weekend. Bye.